Check my microphone. Hopefully you people can hear me. Hopefully you people can hear me. Looks like you can. All right, and you're not in here yet, so you actually can't hear me. Hello, everyone. Come on in. Make yourself at home. All that good stuff. More people coming in. Yay. Still more.
I have a question about the recordings from last week.
Yes, go for it.
Since we weren't able to have a live class session on Wednesday, I believe you were planning to post a couple of videos, and I thought there were supposed to be 2 from what I saw in one of the YouTube videos, but I can only find one shorter YouTube video, and it seems like the one about integration did not upload properly, and I wanted to see if I just was missing it.
Yeah, what day did you check that?
Yesterday.
Yeah, everything worked by then, but let me check.
Okay.
So was the integration one we're looking for?
Yes, I wasn't sure if it might be part of a longer video or if I may be missing the name.
Yeah, let me check real quick. I'm gonna share screen with you. So easy torque calculations, that went up today. Let me see. Did this do anything? Introducing Faraday's law. Elastic collisions. Yeah, I would have thought it would have been in this one, but I'm not really sure. Yeah, I think it would be in this one. Let me check which one I did the integration with. I can check in my notes real quick.
Okay, thank you.
No problem. So 241, that would have been last week. I didn't do any integration on Friday. Yes. So 241 D01C chapter 9 finish. So if I look on these, I look for the one that says D01C, that one should have it. Of course, it's not showing my list like I normally have. No, that's not it either. So easy torque, introduction rotational motion. I think it might be using and calculating center of mass, this video right here. Yes, that's the D01C chapter 8 finish start chapter 9. Well, now that looks like a different one than it should be. Let me see if I got it.
When I watched that one, it seemed like it, I mean, I just fast forwarded through it, but it seemed like it was a full lecture for a different class.
Yeah, that was an entirely different one. I must have loaded the wrong one or something. Yeah, that's just, yeah, that's definitely not the right one. Okay, well, I'll have to fix that. I know I have the video still, so that's not a problem. I will post that immediately after this class. I don't know why that happened, but here we are.
Thank you.
No problem. Sorry about that. Yeah, and I stayed up actually quite late to make sure all those videos went up, and I must have just, because it was so late, might have clicked on the wrong video and posted the wrong one. So I apologize. So anybody else have any other questions? Maybe ones that I can answer in a positive way. All right. Well, we're going to, there's another part in chapter 10 that we're going to work on. And specifically, I want to give you some easy tricks or whatever to talk about torque and how to calculate torque. But then I'm also going to go into solving a more complex problem than you've been doing before, because before we've been only treating masses as if they're blobs of object and didn't consider their rotation with respect to their own center of mass. and we didn't really consider separate objects very much except in a center of mass type scenario. So let's get started with doing that. The first thing I want to tell you though is I want to remind you that in fact this omega thing that we introduced and this alpha thing they're special, and you occasionally will see us write vectors on them, and I need to make sure you understand they're not truly vectors, so they don't behave exactly the same way. So remember we started with that equation from trigonometry that said S is equal to R times theta, and that was sort of our definition of radian angle. And then you could say, well, S is also like basically X, it's a distance along some straight line or along some curved line. So we say that's R times theta, and then we take the derivative of this with respect to time, and we get V because that's what dx dt is. And if R was a constant, we just get R times d theta dt. So we define this to be R times omega. And then later we use this omega as if it's a vector. I hesitate to put it here because obviously it can't be that, right? It can't be equal to V just by multiplying this R times this because it has a weird direction. Additionally, I could take the derivative of this, and the derivative of V with respect to t is just acceleration, that's dv dt. But again, if that R is a constant, then I get d omega dt. And of course, that's just defined as R times alpha. And again, we have alpha as if it's a vector. Okay, so the sense that this is a vector means like this. It's actually called a pseudo vector. Okay, if you imagine something rotating this way, okay, then you take your right hand and you curl your fingers in the direction of that it's rotating, and then your right thumb points in the direction of omega. So in this case, omega would point out of the board. But it is not truly a vector. It doesn't obey the same rules as vectors. So we call it a pseudo vector, Pseudovector. Okay, and that comes into play every now and then. But the main reason is, you remember from depending on how you learned algebra, some students learned algebra in high school by assuming there were these rules, and then they use these rules to teach you how to solve equations. Like you can add 0 to any equation. If you add it to both sides, it's still a valid equation. Or you can multiply one side of an equation by a number, as long as you do it by the other number, by the same number by the other side, then it's okay. Or you can have a distributive property or a commutative property, like A plus B is equal to B plus A, or A times B is equal to B times A, or A times B plus C is equal to AB plus AC. Those little rules. Some people, like I said, some algebra classes use that as if they were rules, and they use them to manipulate equations so that you could solve them. And other ones just like taught you how to manipulate equations to solve them, and then they got later on and introduced these rules, the distributive property, the commutative property, and all that stuff, the identity property of one, the zero property, all that sort of stuff. Well, in reality, what this is that those are general rules that, if satisfied, they define something called a vector space. And when you have a vector space, all the parts of it are called vectors, and you can't combine two vectors to get something outside of the vector space, and it's all special. Well, it turns out these rules are violated by this omega, and I can show you one of them now. For instance, if you have a particle moving to the right with a velocity v, and then you hold it up in front of a mirror, like so, then you look here and you see the image, in fact, is a particle moving to the right. And that's all well and good. And you're like, yay, we're good for that. Well, if you consider that same disk we were just talking about, and we see it's rotating this way, right? That means the part farthest from the mirror is going up and in towards the mirror. And of course, that gave us an omega, according to the right-hand rule, equal to that. Well, if you draw that same disk here, remember the part farthest from the mirror was going up and then towards the mirror. Well, if you do your right-hand rule on that one, that omega is pointing that way. So the fact that they're not the same thing with its mirror image tells you it is in fact a pseudo vector. So that's just something I want you to keep straight. You can also think about it this way. We know V is equal to R omega from that equation right there. Clearly V would be like, that's one particular velocity. That is clearly not equal to R times omega, because omega points this way and V points that way. So there's obviously no direct vector equation that I can give you right there for that. Oh, I just stopped the video for some reason. I don't know how I did it. My arm just touched the keyboard. Okay, so that's the one thing I wanted to get through to you. The other thing that we want to go over is torque. So torque, remember, plays the same role as force in Newton's second law, except in Newton's second law, we had the summation of the forces is equal to either dP over dt, or we had m dv over dt, which are vector equations. Well, in the rotational world, we have the summation of the torques, which also happens to be, in some sense, a pseudo vector, because you can see it comes from a cross product, which has weird things associated with it. But basically, it's not quite as much of a problem there. And in this case, it's going to be I times alpha. And again, that alpha's got that same pseudo vector stuff going on. But we need to calculate what that torque is. So I've given you a couple definitions. I told you, for instance, that torque can be calculated as R cross F, where R is the vector that points from the center of rotation to the point of application of the force. But you can also say torque has a magnitude equal to R times F times the sine of the angle theta between them when they're tail to tail. Or there's another way, R, the perpendicular component of R that's perpendicular to F, or you can say F, the component of F perpendicular, that is. So the component of F that's perpendicular to R times R works as well. So I'm going to give you an example of all three of those, really, just so you can see there's a lot of different ways to calculate torque. And then you just use your right hand rule, R cross F. Remember, if this is your R vector and this is your F vector, and notice they're tail to tail, so that angle is the theta that you want. R cross F means you lay your right hand such that this acts like an axle that is the R vector, so I can turn my hand any way I want to, but I have to stop such that my fingers can curl towards F, using, again, my right hand. When I do that, then I can see that my right thumb is pointing into the page, so torque vector in this case would be into the page, and that's the symbol we use for into the page, is that circle with an X on it. It's like you're looking at the backside of an arrow, just like I used up here, a circle with a dot in the middle. That looks like you're looking at the arrowhead. That's the pointy part that stabs you, and that's the outer edges of the target, or excuse me, of the arrowhead. So let me show you an example. For instance, this R cross F, we know torque is equal to R cross F can be computed by just using a determinant. And that determinant is basically, you put the first row of the vector, or excuse me, of the matrix I, J, and K. That's your first component, first row of your vector, of your matrix. Then the first vector in the cross product is your second row. So I'd put the X component, the Y component, and the Z component of the first vector. And then the second vector goes in the third row, and that'd be F sub X, F sub Y, F sub Z. And then, of course, you can do that method I told you about, where you expand on one of them and then do the determinant of the minor that's left. And in that case, this is the matrix component 1, 1, because it's in the first row in the first column, and you have -1 to the parentheses 1 plus 1 power. That's 2. -1 squared is positive. So I then cover up that row, or that row and that column, and then take the matrix that's left, this little 2 by 2, and do its determinant. So in that case, I'll get R, Y, F, Z minus R, Z, F, Y times I hat. Now this one is 1, 2. It's in the first row, second column. So that's -1 to the 1 plus 2. That gives you -1. The way I deal with that is I just do the opposite, or do the determinant in the opposite order. So I have to cover up this column and this row, And normally what would be left is this, and this, and you do a determinant that way. But since it's negative, I'm going to do a determinant this way. So I'm going to say RZFX minus RXFZ, and that's in the J hat direction. And then finally, we do K hat, that's the 1, 3, 1 plus 3 is 4. So -1 to the 4 power is clearly +1. So I cover up this column and this row, and then I do the determinant of what's left. So I get RXFY minus RYFX, all in the K hat direction. Notice that's a really nice pattern. For instance, as soon as you get the first term in the first one, then you know immediately the second term, because I have a YZ on R and F respectively. So I just flip them to F and R respectively. And then of course, those are both Y and Z. So this one's got to be the one that's left, which is X. So you know that's an I hat. So that's another neat way of doing it. But that's just the brute force way of calculating a cross product. So we don't want to do that. That's not fun necessarily. So what we'd really like to do is find an easier way, and that's what these other versions are about. If you, for instance, take the component of R that is perpendicular to, or excuse me, the component of F that's perpendicular to R, you can see this right here is perpendicular to R. So if I broke F down into this plus this, then I just multiplied this thing times R and I'd get it. Well, this thing is just F sine theta, which is that times that. So that's why I have F perpendicular times R. Similarly, if I drew this line right here, then that allows me to compute the component of R perpendicular to F, which is this one right here. Notice that's just R times sine theta. So if I take this and this, I get R perp and then times F. So that's where all that comes from. So let's look at an example. So here's an example. We're going to imagine that I'm loosening a normal hex bolt, a hex nut, I should say. Okay. And it's actually kind of hard to get loose, not an uncommon problem in everyday life. Okay. And let's say it looks sort of like this. And it turns out this wrench is just not big enough, so I put like a breaker bar on it. So a breaker bar is when you basically put something on that to make the lever arm even larger. Okay. So what I'm going to do is I'm actually going to apply a force. Now this bolt might be in some, and this nut might be somewhere that's really hard to reach. So I have to actually apply a force, say at an angle of 36.9 degrees. And that force might be 100.0 newtons. And when I say 36.9, I say with respect to horizontal. Now the lever arm vector is a vector that points from the center of rotation to the point of application of the force. So this is R, and this distance from here to here is 1 meter. So I have a distance of 1 meter. That's why I used a breaker bar, so I could get, more than 3 feet away from the thing and then apply the force. So this is a good case where you might want to take the component of F that's perpendicular to R. So if I look at this, I normally draw my positive x-axis to the right and my positive y-axis to the upward. So this is actually going to be a negative component, and so is this one. Okay. But you see this component right here is the one that's perpendicular to the R. So I'm going to call that as F perp. Now I see that's 36.9. So that tells me it's talking about the 3, 4, 5 triangle. 36.9 is the smaller angle. So that's opposite the 3. And I see that the magnitude here is 100. In order to get make 5 into 100, I got to multiply by 20, which means I have to multiply by 3 by 20. And it means I have to multiply 4 by 20 newtons as well. So now I can see that this component right here is actually equal to 60 newtons. So I say torque is equal to F perpendicular times R. Well, F perpendicular is 60.0 newtons. And then R, of course, is just 1.00 meters. So the torque comes out to be 60 5.0 Newton meters, which you might remember is the same thing as a joule, but we do not call it a joule. We call it a Newton meter, or in other systems of units, it would be like an inch pound or a foot pound or stuff like that. Yes, Newton centimeter, all those different things. So it's always a unit of force, which is like the pound or the Newton, times a unit of distance, which is like the meter or the inch. Okay. Does that make sense to everyone? That's a pretty straightforward problem, right? Now, when I took my physics class, for some reason, they didn't actually do this other one, the R perp times F. Now, I think they might do that now in physics books, in most physics books. And I know they do it in statics books. So it's really nice because there are instances where R perp times F is a lot easier to get to. So I thought I'd give you an example. So this is going to be example 2. So with example 2, I'm going to imagine being at a sorority house and putting up a capital Greek gamma. Okay. So here's a capital Greek gamma. Looks like that. I'm going to say this point right here is the point of rotation. In other words, we got a bolt stuck in there, and we're going to try to stand this up and then secure it. So that is the center of rotation for the actual system. I'm going to say that this distance from here to here is 5.00 meters. I'm going to say that this distance from here to here is 2.50 meters. I'm going to say that this distance from here to here is 0.500 meters. And I'm going to say that this distance from here to here is 0.500 meters. And that should be enough. But what I'm going to do is imagine that there is a force applied, F equals 100.0 newtons right there, perfectly horizontal. Okay, so the force is acting horizontal. Now, in principle, what you have to do is you have to draw an R vector from here to there. So you draw an R vector. And then in principle, you can compute R times F times the sine of theta, but you'd have to find the angle between them when they're tail to tail, which is actually this angle. Or you could, put it in a coordinate system and make F as a vector and R as a vector and compute a cross product, all that good stuff, all that works. But why do that? Let's just use R perpendicular times F, because I know R is basically starting here and then going all the way over here. So the component of R perpendicular to F is just from here to here. And this is actually the component of R anti-parallel, if you will, to F. But I can see that this is 5 meters and then another 0.5 meters. So I can say this is 5.50 meters is R perp. So torque is equal to R perp times F, just gives us 5.50 meters times 100.0 newtons, which is 550 Newton meters. You could put another 0 there, but that's not really consistent with sig figs. So we got that. And of course, if we did our cross product, we would see, okay, R cross F is going to have to go this way. So it should come out of the page. So I'll write out of page, which means that direction right there. Now, just for fun, let's verify whether we can actually get it from the cross product. So what I'll do is I'll pretend this is my positive x-axis. I'll pretend this is my positive y-axis right there. So I got y-axis pointing up. And of course, a right-handed coordinate system means the k-axis should be pointing straight out of the page as well. So we got to keep that in mind. Now, if that's the case, then my R vector is just going to be up 5.50 meters in the I hat direction, and then it's going to go over what appears to be 2.50 meters minus 0.5 meters. So it'll be plus 2.00 meters in the oh, actually this one was the J hat direction. Sorry, I wrote that backwards, and this one's in the I hat direction. Everybody see what I did there? Anybody have a problem with that? The whole way across here is 2.5. But that started from 0.5 meters this far. Again, assuming basically the same width throughout, which I didn't actually write down here, but it's what I meant. So that distance being 0.5 meters just means I'm going to take 2.5 meters and subtract from this little distance, and that'll give me the 2.00 meters. Now the F, on the other hand, the force is going to be 100 newtons, and it's pointing in the negative X direction. So I'll say negative 100.0 newtons I hat. So I can do my torque is equal to the determinant of I hat, J hat, K hat. My R is going to be 5.5 and 2 and 0. And then my F is going to be negative 100 and then 0 and then 0. We can see when I do the I hat one, all that's left is 0 times 0. When I do the J hat, I get 0 times 0. And in fact, the only one we get a full one is when I do K hat. And of course, I cover up this column and this row, and I do 550 times 0, that's 0, minus 2. Oh, I wrote this backwards. Remember, I made the mistake when I wrote this here. This was supposed to be the Y component. This is supposed to be the X. Glad I caught that now. So remember, the X component was the 2.00 and the Y component was the 5.50. So when I multiply with the K hat, that means I cover up this column and this row. So I got 200 times 0, or excuse me, 2.00 times 0 minus 5.500 times negative 100. So that minus a negative beats plus a positive. So I'll get positive 550 Newton meters. This one had newtons, this one had meters, and that's in the K hat direction, which is, as we said, for a right-handed coordinate system, that's out of the page. So that's completely checks with that one. Any questions on that? That little trick can save you a lot of trouble just by looking for the component of R that's perpendicular to F. And sometimes they do it like grade school things where you have to subtract things to get actual lengths and stuff like that. And that's good practice for you. That's the kind of stuff you should be able to do. So anyways, anyone have any questions on that? All right. So now that I've covered that, and we did last time, we did some kinematic equations, which really are the low-hanging fruit of this chapter. It's just using basically the equivalent of 1/2 AT squared plus V0T plus X0, and V0 squared, or V squared, is equal to V0 squared plus 2AX minus X0, only with rotational coordinates. Your book has plenty of examples doing that. I worked one pretty good one that had a lot of things to calculate. So I don't feel like we need to spend any time doing that. What I'd like to do is spend a little time doing a more complex Atwood machine. So what I'm going to do is I'm going to imagine an Atwood machine that has a pulley that is not massless. So here's a pulley, inner radius RA, and then attached to that or fixed to that rigidly, it might even be milled out of the same chunk of aluminum, say. If you have that, then this radius I'll call RB, that's the bigger one, okay? And by writing it down, I'm saying I know that one. I'll say that they're both cylindrical, so that the moment of inertia of this would be 1/2 the mass of the inner one, M sub I. Actually, I could call it MA. Yeah, let's call that MA. What the heck? 1/2 MA RA squared plus 1/2 MB RB squared. You'll see later when we do an actual integration to calculate the moment of inertia by calculus that for a cylinder, the moment of inertia is just 1/2 mr squared, and that's what I'm using there. It doesn't matter. I'm not even going to make use of this. I'm going to keep it as I in this problem, but by writing it down, you can assume I know I, and therefore I'm going to know MA and RA and MB and RB. Okay. Now I'm going to hang from the inner cylinder a mass big M and hang from the outer cylinder a mass little m. Again, so we're assuming we know all of these. What I want to do is, assuming we know MA, RA, MB, RB, M, and I thought there was something else, and I. What are the acceleration for the object on the right, which would be over here, the acceleration for the object on the left, which would be over here, the angular acceleration, the tension in the left, and the tension in the right. Okay, so that's the problem we're going to solve. So just like we did the Atwood machine before, we're going to make free body diagrams so that we can apply F equals ma. So we know the summation of forces is equal to mass times acceleration, but now we got the added one, the summation of the torques is equal to I times alpha. What I'm going to do is establish that I'm going to pretend, since m is big, that we think this thing's going to go down. So I'm going to just, for good reason, call the positive direction big M going down. That means little m going up is also positive. That also means the pulley spinning counterclockwise is positive. And then, of course, all the opposites of that are true as well. So here's my free body diagram stuff that I would like to work. So first off, I'm going to draw a dot to represent the mass big M. And in fact, since I'm calling big M going down as a positive direction, I'll write that vector as green mg, and then I'll just put down here a positive to let us know what that means. Now, according to this mass, it feels like it wants to fall at a rate of 9.80 meters per second every second, but this rope is slowing it down. So it senses the tension in the rope as if pulling upward on it. And that, of course, is the opposite of the positive direction. So I'm going to put that in red, and that tension is going to be called T sub L. Now, the reason T sub L has to be labeled separately from T sub R is because this tension right here is going to be responsible for rotating this pulley, and lifting the mass M, whereas this tension over here is only going to have to lift the mass M, little m, that is. Okay, so that's why we expect them to be different, unlike the Atwood machine. So from this one, I can say mg minus TL is equal to m, big M that is, times A sub L. And that's going to be my equation 1. Now I'm going to do a free body diagram for the mass little m. Again, big M going down is consistent with little m going up, so I'm going to call up the positive direction there. And according to little m, it would probably fall if it wasn't for this mass pulling it up, or for this rope pulling it up. So in fact, that is T sub R, and that's pointing in what I called the positive direction. Okay. But the object's weight is slowing it down, so we have a force of mg pulling down on it. So in this case, I'm going to get a free body diagram that gives us a F equals ma of T sub R minus mg is equal to m times A sub R. Okay. I had to mess with it. Just had to mess with it. That's going to be equation 2. Okay. Now I've got a free body diagram for the pulley. I'm going to draw a little bit, not to scale, obviously. And I'm not even going to worry much about getting it centered, clearly. So in this case, remember, big M going down is consistent with positive. So I want to stick with that with my torques as well. So that's counterclockwise torque. Like I said, in the statics class, you can classify all this just, or clarify all this just by doing this and putting a positive around it. That just means right, up, and clockwise, counterclockwise rotation are all positive. So in this case, I'm going to say, according to the pulley, this rope right here is pulling on it with a force of T left, whereas this pulley over here, or excuse me, this rope over here is trying to slow it down by pulling with a force of TR. And of course, the free body diagram for this allows us to calculate the tension. Remember, this little quantity right here is RA, whereas this quantity right here is RB. So my torque becomes RA times TL minus RB times TR is equal to I times alpha, and that's equation 3. Remembering, of course, that I is just given by that formula up there if we ever need to simplify it. Okay, I'm not going to mess with that, but it's something you can do later if you want to. Okay. Now we want to look and say, what exactly are our unknowns? Well, we don't know TL, we don't know AL, we don't know TR, we don't know AR, so that's 4, and we don't know alpha, so that's 5 unknowns. Well, with 5 unknowns, you need 5 equations. Well, it just so happens to be that, notice I didn't have to label this alpha left or alpha right, it's just plain alpha. And in fact, if you rotate this 1 degree, then you're automatically rotating this inner pulley 1 degree as well, because they're made all together. So the alphas, in fact, are set. They're fixed to a certain quantity. But that alpha is directly related from, remember, A equals R times alpha. So I can actually make, I'll call it equation 4, but it's really like equations 4 and 5. What I'm going to do now is say that alpha, which is really just A over R, because A is equal to R times alpha. So it's A over R. So in the case of AL, it's AL, which is the left side, over RA. So that's one equation. And then, of course, that alpha is also equal to AR over RB. So that's another equation. But together, I'm just going to call that equation 4. And just realize it's really more than one equation. It says how AL and AR are related, but it also says how alpha is related to either AL or AR. Okay. Well, with a little bit of practice and experience, you can sort of find the best way to solve this. What you ideally want to do is sort of use what I call good algebraic hygiene. So you want to make sure you're stating exactly what equations you're using so you can look back later and find out whether you made a mistake with whatever M, say, came from equation 2. If you took the time to state using equation 2, you know the M was little m. So that can keep you from screwing up, and it can check to make sure you use, in fact, all 5 equations, because if you accidentally made some algebraic error, but only use, say, 3 of the equations, you might actually get a solution, but it's impossible to get a solution unless you use all 5. So by doing what I said was practicing good algebraic hygiene, you'll know whether or not you've used everything. So here's my plan. My plan is I have a torque on the left-hand side, I have a torque on the right-hand side, and I got an equation for that relates to torque on the left-hand side. I got another equation that relates to torque on the right-hand side. And those are in terms of AL in the left case and AR in the right case, but there's a relationship between AL and AR. So if I could figure out some way to solve for RA times TL in terms of just one of these A's, and then do the same thing in terms of that same A, and then do the same thing in terms of that alpha, then I could get an equation that's only related to A sub L, say. So that's what I'm going to do. So first, I'm going to take equation 1, and I'm going to solve it for T sub L. Doing that's pretty straightforward. I get T sub L is equal to big M times G minus A sub L. I'm going to call that 1 prime. Now I'm going to multiply one prime by, well, it's TL, and I see the TL is multiplied by RA, so I'm going to say RA. So this time, I'm going to get RA times TL is equal to M times G minus AL. And of course, that's also times RA on this side. Should have left myself a little bit more room. Okay, so that'll be equation 1 double prime. Now I want to do the same thing with 2. So what I'm going to do is I'm going to solve for TR. That'll give me, let's say TR is equal to M times A sub, well, I can write it that way. I can say, because it's going to become positive over here, I'm going to say that's G, whoa, Nelly, right off the board. That's positive when it comes over here. So I'll say G plus AR. And that's going to be equation 2 prime. But I want to multiply this by RB, but I also want this in terms of AL, not in terms of AR. So I'm going to multiply by RB and plug in 4. So when I do that, I'm going to get RB times TR is equal to RB times little m times G plus. Now, if I want AR, basically AR is going to be RB over RA times AL. So that's going to be my equation 2 double prime. So this is really good for me. I know now an expression for RATL and an expression for RBTR, and they're only in terms of AL. So I can put them in here and I'll have AL all on this side and I'll have an alpha on here, but alpha is just AL over RA. So I'm going to plug 1 double prime, 2 double prime, and 4 into 3. So plug 1 double prime, 2 double prime, and 4 into equation 3. Easy peasy, right? So when I do that, I'm going to go to, I think I'll write with my blue pen now. So what I'm going to do is I'll say RATL. So RA times TL we see is this. So I'm going to say RA times big M times G minus AL. Now I got to do minus RBTR. So I'll say minus. Now RBTR is RB little m G plus RB over RA times AL. And then of course that's all equal to I times alpha. So I, and now I'm going to make use of the fact that alpha is AL over RA. So now I've done all that stuff I just said I was going to do. So what I want to do now is distribute, in other words, get rid of all these parentheses and then put all the terms with AL on one side and put all the terms without AL on the other side, and then I'll be able to solve for AL. So when I do this, I'm going to say RA MG minus RA big M AL. I'll put a dot there just so I'll remember which one has an AL in it, minus RB little m G minus and plus, that'd be minus RB little m RB over RA AL. I'll put a dot over that one too, to remind me it's got an AL in it. And that's 1, 2, 3, 4. So that's all 4 of these terms. And then over here, I've got a I over RA times an AL. So that's got an AL in it as well. The AL is positive on this side, and these are negative. So I'm going to pull them over there. What I have left on this side is RA times M. Notice they all have a G in it too, so I'm going to factor that G out. So RA times a big M minus RB times a little m. That takes care of this guy and this guy. And then all that times G is equal to, now I'm going to say I over RA. All of them are going to have a sub L in it, so I'm going to leave that off. So that took care of that one. This one's going to become positive over here, so I'll say plus RA times big M. Took care of that one. And then I'll say this one's going to become positive too, so I'll say plus RB times little m times RB over RA. And that takes care of that term. And all these have an AL multiplied by it. Now, for best results, it's actually wise to multiply through by RA on both sides. And that'll get rid of the complex fractions, basically. So now I'm going to get RA squared. I'm going to put the M in front of it because that's normally the formula we look for in moment of inertia. It's MR squared. So if I put the M in front, that can help me keep track of what the units are supposed to look like. And then I'll have minus M times RA RB. All of this times G. Notice that's M times a length squared, M times a length squared times a G. So that all works. This side, the RA is going to cancel out with that RA, and I'm just going to get I. Here I'll get plus M. Again, I'm putting the M's first, RA squared. And then I'm going to put plus M. Notice the RA here is going to cancel out with the RA here, so I'm just going to get RB squared. And then all of this times A sub L. So finally, I can write A sub L is just equal to M RA squared minus M RA RB over I plus M RA squared plus M RB squared, all of that times G. So we found one of our accelerations. And look, as you take the limit, as I goes to 0 and RA goes to RB, which both go to just plain R, notice what happens. The I goes to 0, 0, that's just going to cancel out. This becomes R squared, this becomes R squared, this becomes R squared, this becomes R squared. So I end up getting A is just M minus M over M plus M times G, which is exactly the Atwood machine expression for acceleration. So that gives me a great deal of confidence that I did it properly. Does that make sense? Now, if I want AR, all I got to do is say, well, AR, remember, we used as just RB over RA times A left. So A left, or excuse me, so AR should be, I'm going to divide by an RA, but multiply by an RB. So this is going to become M times RA RB minus little m times RB squared. Such beautiful symmetry in this, I love it. And then the denominator will stay the same. That's M R big A squared and plus little m R big B squared, all that times G. And I now have an expression for the acceleration on the right-hand side. Again, if you let that I go to 0 and RB equal RA, then you're again going to get M minus M over M plus M times G. So that's another nice check. It gives us back the results that we had already known in the simpler case of basically having a massless pulley. Any questions on that? Now we can go ahead and go from here and actually figure out what TL and TR are, as well as the alpha. And the alpha is actually probably the easiest one to get, but we're going to have to make use of the stuff we already know, which is these two things. Well, the other thing we're going to have to make use of is our equations for TR and TL. So I'm going to make use of the TR here and the TL here. So to do that, I'm going to go ahead and record number 1, and let's call this 1 star. So equation 1 star is going to be this equation right here solved for TL. So you can see TL is going to be equal to M times, notice this will be mg when I pull that over there. This will be positive t, but this will come over here as negative. So I'm going to say m times g minus al. So that's what TL is. And I'm going to take 2 and call it equation 2 star, and I'm going to solve it for TR, and that one's a little easier. So TR is going to be on this side, and the mg and the ma will both be on this side as positives. So I'm going to see it's just m times g plus ar. So that's our equation 2 prime. Now that I have that, I can also make use of our accelerations to calculate what the tensions are. So let's start off by calculating exactly what TL is. So TL is equal to m times g minus m. Now I'm using that AL up there. So that AL up there is not beautiful, but it's okay. I mean, it's got pretty symmetry. But that means it's just going to be a little bit of algebra to deal with. So again, I'm thinking get a common denominator. I don't need the A's right now, so I'm going to pull them out of the way a little bit and just work from here. So if I get a common denominator, obviously the G's already in there, so I'm just going to deal with this M, and this M times each of those terms is going to give me I times big M plus big M squared times RA squared plus little m big M times RB squared. Notice all the units work out. This has units of MR squared, and then there's an M, so it's M squared R squared, M squared R squared, M squared R squared. So all those units are working out right. And now I'm going to distribute this M and this negative for the other part of the numerator. So I'll say minus M squared RA squared. Minus minus becomes plus, so I'll say M big M RA RB. All that over the same old boring denominator, which is actually a nice denominator because notice the big M is with the big radius and the small m is with the small radius, which is exactly what you expect. And then of course, all this is times G. Now, when you look at that, you can see there might be some cancellations. In fact, I got an M squared RA squared minus M squared RA squared. So those two are going to cancel out immediately. And then I got an MM and an MM, but the R's are different. So I can finally go ahead and write what T is. So I'm going to say TL is actually going to be equal to I times M time, plus M times M RB squared plus M times M RA RB, all that times G over I plus M. Ooh, that's supposed to be a big M. Big M RA squared plus little m RB squared. So that's the tension in the left-hand side. Now remember, in the Atwood machine, the tension was 2mm over m plus m. So if I let I go to 0, these two terms are going to disappear. And if I let the r's all be equal, then I got a common factor, r squared, r squared, r squared, and r squared. So I'm going to get mm plus mm over m plus m. So in fact, as t goes to 0 and ra goes to rb goes to just plain r, then TL goes to 2mm over m plus m times G, which is exactly what we got for the Atwood machine again. Now I'm going to do TR. And of course, TR is just equal to mg plus m times AR. So I can again make use of my AR. So I'm going to say M, and because I know I'm going to get a common denominator, I might as well say IM. So that's the little m times the I. And then the little m times the big M. So it'd be plus little m big M RA squared plus little m squared, that's the little m times that, times RB squared. And then I'm going to have these two parts of the numerator. So I have plus, because it's A plus G, I'm going to have plus little m times big M, RA, RB, and little m times little m with a minus, so that's m squared, RB squared. Of course, all that will be times G, and then all this will be over I plus big M RA squared, or RA squared, right? No, RB squared. I've been writing that backwards the whole time. Plus MRB squared. I need to check that because I was pretty sure the big M was supposed to be with the RB and the little m was supposed to be with RA. The algebra is basically right, but I'm wondering if I didn't switch my big M with my little m somewhere. So we'll go over that in a second. Ultimately, though, that gives me TR is equal to, notice the IM is going to survive, MRA squared, MRA-RB, no, but the M squared RB squared does cancel out. So that will cancel out with that. And I'll get plus MRA squared plus MRA-RB, all that divided by I plus MRA squared plus little m RB squared. Really bothered by that RB. I was getting excited because I thought they were matching, but now it seems like they didn't. So I got to double check that. Anyway, so there's our TR. Now I've got the accelerations and both of the tensions. Now I just need alpha. And of course, alpha is the same thing as AL over, we found earlier. Alpha should be AL over RA. So AL over RA. and the left-hand side was the RA and the right-hand side was the RB. So I know that's not where my problem came in. Now I just have to take my AL, which I have right here, and divide that by RA. So I'll get alpha is equal to M just RA minus M just RB over I plus, again, MRA squared plus little mRB squared, all that times G. Again, in the limit as I approaches 0 and RA approaches RB approaches R, then alpha just approaches M minus M over M plus M, all of that times R G, which is exactly what you expect. It looks just like the Atwood machine, except it's got that extra factor of R to make the units radians per second, as radians per second instead of radians per, or excuse me, instead of meters per second. So that's it. Let's look back real quick and try to see what might have happened with my M. So when I did equation 1 prime, so this will actually show you the good algebraic hygiene stuff that I was telling you about. So when I did equation 1, that was regarding big M. So I had a big M, TL. When I did equation 2, that was little m. So those are all good. And when I did this, I had no m's whatsoever. This gave me big M for 1. This gave me big M for 1. This gave me little m for 2. This gave me little m for 2. So that all looks good. So then I took this, which is RATL, which is this one. That should be the big M. So RA times M, the big M, times G minus AL. And then RBTR, that was this guy. So that should have been a small m, RB, small mg. That all looks good. My AR was replaced with RB over RA times AL. That looks good. And then, of course, my alpha was replaced with AL over RA. So that all looks good. Then when I grouped all these terms together, I had RA times big M minus RB times little m. That all looks good. When I did over here, I did, here's the one with the acceleration in it. So big RA times big M and RB times little m. So RA times M is good, and RB times little m is good. So I've actually got it right there. M with the big RA, excuse me, big M with the RA and little m with the RB. So that's all good. It looks like I copied it wrong when I went from here. I had it right 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 here. Big M with RA, big M with RA, big M with RA, big M with RA. Wait a second. Okay, so it was right. Yeah, RA was my small one. That was the big M. So yeah, okay, everything was right. Sorry about that. I guess I got confused which one was RA and which one was RB for a second there. So RA is the smaller one, and that's with the bigger mass, and RB is the bigger one with the smaller mass. So yes, that all works. Any questions on that? That was a lot of algebra. That's not a trivial problem. You would probably initially prefer to work that with numbers, and that'd be fine. And I'd say that's maybe sort of like your holy grail of problems for this particular chapter. I think the only thing that could make it more complex is if I added a friction force on it, which in this case, the friction force would actually be applied here because there'd be a friction force on the actual pulley that causes a separate torque, say. But you could do that. But you'd have to, in that case, decide which way, based on the numbers, which way it really is rotating, and then the tension, the friction force would act in the opposite direction. So that'd be really way more complicated. But I would say state all these values as if you know them. Just make up some numbers. You know, make big M much bigger than little m. So maybe call this 100 kilograms and call this one maybe 20 kilograms, and then make RA, you know, a meter, and RB 10 centimeters or something like that, and try to solve this outright that way with numbers. And I think you might find that it's a lot easier. But if you could do it this way, you'd be even better off. So I definitely recommend you trying to do that as a excellent practice problem. You will have this video. It should be posted by tonight, barring any problems, but you know how that is. Like I said, I did post something that didn't work out so well. We've only got about 10 minutes left, so I thought I'd work on using I equals the integral of r squared dm. So the deal is, just like we did when we were doing center of mass, the integrand here is r, and in fact it's r squared. So what you want to do is choose a differential mass element whose value r doesn't change appreciably over the entire size of dm. Okay, so let's in order to keep that in mind, or in order to show you what I mean by that, let's put right here the x-axis, let's put the y-axis, and let's imagine a thin rod. So here's a thin rod, and thin means its y dimension is really, really small. Okay, so there's my thin rod. Let's say the length of this is just L. Let's say its mass is big M, and therefore we know lambda, which equals dm over dl. This is something that's going to come up over and over and over again. If it's uniformly distributed, that would be a constant. So what I'm saying here is your dm will take one of three forms. Dm will equal lambda times dl, or it will equal sigma times dA, or it will equal rho times dV. Now this lambda, the sigma, or this rho don't have to be uniform. You know, they're all going to be obeyed by an equation like this. So sigma would be dm over dA, and rho would be dm over dV. But once they're a constant, then you know they're something pretty simple and you can work with it. But I could say lambda is equal to some constant k times x squared. And that would represent something that's getting a lot heavier the further you go away. So at L over 2, the mass per unit length might be m over L, but at L, it's going to be 4 m over L. So that kind of thing could help you model what you're actually dealing with. So I want r, the distance from the point at which it's rotating, which is this point right here. It's going to rotate this way. I want r to vary very little over the distance. So because this isn't very thick, then this distance right here, which is just dx, doesn't have a huge variance in r. Notice r is the sort of shortest here. It's equally long on each side, but it shouldn't be very, very different. That's why I made it a thin rod. So what I'm going to say is I'm going to say this little guy is dm, and it's actually equal to lambda times dx. So I, which equals the integral of r squared dm, is just going to become, notice r is just the same thing as x in this case. So I'm going to say the integral of x squared times lambda dx, and I'm going to integrate from x equals 0 to L. In doing that, I'm going to get lambda out in front, and then I'm going to get 1/3 x cubed from 0 to L. So I'll get 1/3 lambda L cubed. But lambda, notice, is just m over L, because the mass is m and the length is L. So I can now say we get 1/3 m over L times L cubed, which gives me 1/3 ml squared. So I for a rod about the end is equal to 1/3 ml squared. Notice it does have units of kilograms times meters squared. That's what we expect. This will be entirely different when you start to do dynamics, by the way. They're going to have a different unit because they don't want that. They need to be able to account for the fact that density changes from spruce, pine, fir to pine to juniper or whatever. Okay. So that was another example. I think this was example 4. Anybody have any questions on that? Well, let's try it this time across the center. So this will be example 5. So now I'm going to say that this object is along the x-axis, and it goes from negative L/2 to positive L/2. It's still very thin, and its mass is still m. So lambda is still m/L. And what I'm going to do is say this is dx, that little distance there. So this object dm is just equal to lambda dx. So I is going to be equal to the integral from negative L/2 to L/2 of x squared lambda dx, which equals lambda over 3 times L/2 to the third power minus negative L/2 to the third power. I'm going to put an m/L for that. So I'm going to say equals 1/3 m/L. And now I'm going to get L cubed over 8 minus a negative, that's plus L cubed over 8. So that's 2L cubed over 4, which becomes L cubed over 2. So this is 2L cubed over 8, which becomes L cubed over 4. So I'm ultimately going to get 1/12 ml squared. And if you look in your table on moments of inertia, which I want to say is on like page 260, you'll see that that's exactly the expressions we got when we were, or what they have in that table. So in this case, I just integrated from negative L/2 to positive L/2 and got 1/12. Oops, I wrote 1/2. It's 1/12 ml squared. Sorry about that. Here's one final example since I got a couple minutes. Let's do a cylinder. About its center of mass, about an axis through its center of mass, I should say. Okay, let's say its radius is big R. Let's say its mass is m, and rho is a constant. And in fact, rho will be equal to m over pi r squared times h. Okay. So again, I is equal to the integral of r squared dm. I don't want that r to vary on any more than infinitesimally from one edge of dm to the other. So what I'm going to choose is basically this little shape right here, which I think you can tell if I laid it out as a rectangle, it would be approximately 2 pi r by h. In fact, it would actually be 2 pi r plus dr. But anyways, we're going to say that's roughly 2 pi r dr times h. So our differential mass element dm is going to be equal to rho times 2 pi r dr times h, because the thickness of this is dr. So I get the integral 2 pi r squared dr times h. That h is going to come out in front anyway, so I might as well put it there. So I'm going to say 2 pi, and also the rho. So I'm going to say 2 pi rho h times the integral of r cubed dr, and I'm going to integrate from 0 to big R. That's going to be 2 pi h. Now rho, remember, was m over pi r squared h. So that's what rho is. And now I'm going to get the integral of r cubed, which is 1/4. So I'll say 1/4 r to the 4th. You can see these two of these r's are going to cancel out with that. This pi is going to cancel out with that. And I end up getting 2 over 4, which is 1/2. This h is going to cancel out with this h. So I get 1/2 m r squared, which is what I advertised earlier for a cylinder. So you can see, yes, the cylinder has a moment of inertia 1/2 mr squared, and time just ran out. So if you have any questions, please stick around and ask. Other than that, you're free to go. And I will see you all on Wednesday.
I just wanted to check on the due dates for our chapter 10 homework, since we just started covering that today. Is it correct on MyLab Mastering that our chapter 10 conceptual is due this Wednesday?
Yes, yes, you've got everything you need for the conceptual part now. And the Sunday will be the regular part, chapter 10 will be due.
Okay, thank you.
Okay, no problem.
Can I ask you a non-class related question?
Yes. Do you need me to stop recording because it's private or something?
No.
Okay.
I am I'm in differential equations right now, and we're talking about damping.
Oh yeah.
And I just need real life examples of underdamped, overdamped, and critically damped. So I have some. I just wondered if I could run it past you to see if I'm getting it right.
Yeah. Let me let you share your screen with me. Yeah, and our book covers that. I think it's chapter 15, by the way.
I think. Okay, that should be the right thing.
Yep, that's it. mx double dot, that's the ma. The bx dot is the b times velocity, and the kx is the Hooke's law.
Ah, okay, that makes sense.
Yep.
I can't tell if I shared the right screen. What are you seeing right now?
I'm seeing prompt number 5, damping solutions.
Okay, good. Okay, so for my real life applications for an underdamped system, I had musical instruments like a guitar.
Okay.
Would that be true?
I would say that one's sort of hard for you to grasp, but if you get it, that would be fine. It definitely does, just by the weight of the material. For instance, if you're talking about a tuba or a bugle or something like that, the weight of the material does damp it. But I think you might be trying for something that's a little less visible. Whereas, have you ever seen those doors that waitresses use at restaurants?
Yeah.
That is a much better example of underdamp, when they swing all the way from one side back to the other side, back to the other side, back. That's underdamped.
Okay, that makes sense. I think we actually talk about that a little bit lower down. And then for overdamped, I have like a soft closed door, like those automatic closed ones.
Exactly. That's a perfectly,
okay.
That's a good overdamp one. Mm-hmm.
And then for critically damped, I have like a tachometer in your car where it goes up and then goes right back down.
Oh, that one That one could be, but it all depends on the mechanism of the actual tachometer. Is the tachometer tying to the engine, or are you hitting a peg in the dashboard that's stopping it? Because the nature of critically overdamp is basically you don't have any sinusoidal term. You just have basically a linear function mx plus b or mx plus b or whatever times e to the negative xt. So it doesn't have that sine component. That's what makes it critically overdamped.
Gotcha.
So, yeah, I'm trying to think a more everyday example of what that would be.
Yeah, I was trying to read about some and they all seemed a little beyond my understanding, I guess.
Well,
so I didn't.
How about
Didn't
a
go for
car door?
those.
Have you ever found that spot in your car door where you go to close it? It's like midway between opened and closed, and you give it a little push and it just won't do anything.
Yeah.
Yeah, that little spot is more like a critically damped one because you give it a push and it's just going to hit that and come to a stop. It's really,
Oh,
yeah,
okay.
that's probably a good example of a critically damped.
Okay, that makes sense. Thank you.
No problem. You might, like I said, read over the chapter 14 or 15, wherever they covered it there. Sometimes hearing it from a physics book and from a differential equation book. So I'm assuming you're probably using Ross or something like that.
Yeah.
Sometimes those two are really help each other, complement each other well.
Yeah, I was kind of looking at like engineering type examples because those just make more sense to my brain. So
Exactly.
yeah, that's a good advice. Thank you.
No problem. Tacoma Narrows Bridge. That's a good example.
I saw that one too. And we talk about it all the time, but to actually like watch the video of it is pretty crazy.
Yeah, it's insane what that thing did. Anything else?
I had an issue with class enrollment, so
Okay.
I don't know if you want to stop the recording or.
Okay, let me go ahead and kill that for you.